Operations on real numbers. In this module, you will learn some operations on real numbers. You may know that if we add, subtract, multiply or divide two rational numbers, we get a rational number. Now let's check if we always get the irrational number when different operations are performed on them. Look at these examples which show the addition, subtraction, multiplication and division of two same irrational numbers. We see that answer is rational or irrational number. This helps us to generalize that if we add, subtract, multiply or divide two irrationals, the result may be rational or irrational. Now let's see what happens when we perform different operations on a rational and an irrational number. Let's add 7 and square root of 5. We know that square root of 5 is equal to 2.236 and so on. So 7 plus square root of 5 is the irrational number 9.236 and so on. Likewise, 7 minus square root of 5 is the irrational number 4.764 and so on. This helps us to generalize that the sum or difference of a rational and an irrational number is an irrational. Let's multiply 7 by square root of 5. It is an irrational number 15.652 and so on. Similarly, on dividing 7 by square root of 5, we get the irrational number. This helps us to generalize that the product or quotient of a non-zero rational number with an irrational number is irrational. Now let's learn about another operation, which is square root of real numbers. If a greater than 0 is a positive real number, then square root of a equals b, means a equals square of b and b is greater than 0. Now let's learn how to find square root of positive real numbers geometrically. Suppose we need to find the square root of 3.5 geometrically on a number line. First, draw a number line. Mark a point A on it. Locate another point 3.5 meters away from the point A and mark it B. Locate another point 1 unit away to the right of B and mark it C. Now draw a perpendicular bisector of AC to locate its midpoint. Mark it O. With O as center and OC as radius, draw a semicircle. Through B, draw a perpendicular to intersect the semicircle at D. Now, BD represents square root of 3.5. Next, with radius equal to BD and B as center, draw an arc to cut the number line at E. The point E represents square root of 3.5. Let's understand how BD equals square root of 3.5. If you join OD, then OD equals the radius of the semicircle, that is 4.5 upon 2 units. Now OB equals 3.5 minus 4.5 upon 2, that is 2.5 upon 2. Applying Pythagoras theorem to the triangle ODB, we get BD square equals OD square minus OB square. Substituting the respective values of OB and OD in the equation, we get BD equals square root of 3.5. Now let's define nth root of a real number. If a greater than 0 is a real number and n is a positive integer, then nth root of a equals b, means a equals b raised to the power n and b is greater than 0. Note that this symbol is known as a radical symbol. Now let's look at some identities related to the square root. If a and b are positive real numbers, then first, square root of ab equals square root of a into square root of b. Second, square root of a upon b equals square root of a upon square root of b. Third, square root of a plus square root of b the whole into square root of a minus square root of b the whole equals a minus b. Fourth, a plus square root of b the whole into a minus square root of b the whole equals a square minus b. Fifth, square root of a plus square root of b the whole into square root of c plus square root of d the whole equals square root of ac plus square root of ad the whole plus square root of bc plus square root of bd the whole. Sixth, square root of a plus square root of b whole square equals a plus 2 times square root of a b plus b. Now let's learn how to rationalize a denominator by an example. Suppose we need to rationalize the denominator of 1 upon square root of 2. To make the denominator of the given expression rational, we need to multiply the denominator by square root of 2. So, to get the equivalent expression of 1 upon square root of 2, we multiply its numerator and denominator by square root of 2. We get square root of 2 upon 2. It is easy to locate this form of 1 upon square root of 2 on the number line, as it is halfway between 0 and square root of 2. Thus, locating an irrational number on a number line is always easier if it has a rational denominator. Let's see how we can use different identities to rationalize the denominator. We need to rationalize the denominator of 1 upon 2 plus square root of 3. We will use this identity to make the denominator rational here. So, multiply and divide given expression by 2 minus square root of 3. Simplifying, we get 2 minus square root of 3 upon 4 minus 3, which equals 2 minus square root of 3. In this module, you have learnt some operations on real numbers.